Hello, lovely internet people. Good time zone. It's my 10th episode. I have a cat on my lap, and I have an equation sheet on screen. It's a good day. Speaking of equation sheets, I want to point something out. For twice now, I have written some variant of this equation, once incorrectly, once correctly, and I have failed twice, both times, to describe the name and the significance of it. This is Kepler's second law, and it states that all objects in orbit sweep equal areas over the same amount of time, regardless of where they are in their orbit, which is actually fairly significant. But we're not going to be spending much time on that. We've already touched on it a few times. Instead, I want to take a look at the equation sheet here. If you have been keeping up with the series from the start and you've been lazy, you've probably been making your own equation sheet. If you're not lazy, then you're probably willing to go back through the series and rewatch all my videos. If that's something that you're planning on doing, that's fine. You won't hear me complain about the extra engagement. Go you. But I figured that for convenience, I may as well have an equation sheet here to refer to every now and again. And we can just build it up throughout the series. Doesn't that sound lovely? So, turning our attention to the contents of the equation sheet now, we have our momentum, our energy, we have a couple of radius equations, we have a couple of eccentricity equations, time, but what we do not have is, well, let me write it down over here. We do not have velocity, which is really more of a white lie. It's speed. Oh, bye. The cat just got off my lap. It's really more of a speed because it contains the magnitude values for sure, but it does not contain the directional values. I'm not sure, I don't quite remember why I started describing it this way, but I do recall that in class, while I was learning this material, I would be referring to it as velocity instead of speed. And you may have already noticed this in equations like, well, the energy equation here, where I have v squared. It's not s squared, it's v squared. So just little things like that. I figured I could try to reprogram my brain and call it speed throughout the rest of the series. But if I slip up once, then I have to put in know about it. Or I could just continue calling it velocity and put in this overly exhaustive disclaimer at the beginning. And that's the one that I decided to go for. So speaking of this equation here, this energy equation, we have two equations for energy that use two distinct sets of variables. So we have two different equations with two distinct sets of variables, and we can probably use that to our advantage over here in determining velocity, because velocity is one of those variables. So let's write that in here. Let's put in the variant that we found first. So v squared by 2, our kinetic, minus our potential. And that is going to be equal to minus mu over 2a. Excellent. Now we solve for v. So we have v squared by 2. And if we add mu by r to both sides, then we get rid of it on the left-hand side and add it to the right-hand side. That's what we want. I'm going to I'm going to move the mu outside at the same time that I do this. So equals mu times 2 over r minus 2 over 2a. The 2's will cancel. I'll write that down here. V squared, no, not V squared. Not V squared, just V. V is equal to the square root of mu times 2 over r minus 1 over a. And that really is that simple. There's our velocity. So we have enough other components just over the last several episodes that we've done this. We can verify it. So let me put that together for us really quick. All right. So same as it always has been. We're in orbit around the Earth. Our orbit's size is 20,000 kilometers, our semi-major axis. And we are at a radius of 16,365 kilometers and change. So let's plug that in. Square root of 3.986 times 10 to the 5th. I'm not going to bother with units up here because it is going to get cramped if I do. I'll do that here in a little bit. 2 over 16,365.424. Nice. Made it fit. A is 20,000. 1. Sometimes I'll do it that way, just so that it looks neat on the page. Anyway, if you solve for this, you will get 5.36. And for units, we have square root of kilometers cubed per second squared times per kilometers minus per kilometers. The rules say that because these are the same, they can be combined to become per kilometers. So we can subtract one of the kilometer exponents. Then we have kilometers squared per second squared. Square root of that gets us kilometers per second. Happily, the units work out. All right. Is it? Is that what it is? So if we go over to our specific orbital energy page, scroll down, let's go down to the example that we've been using before. This is the number that we put in, and if you do the math of this, just square root of 1 squared plus the other squared, you will actually end up with 5.36 kilometers per second. Nice. Give us some space to work. All right, so we have this new equation. Let's play around with it. All right, so what are some of the limits that we can put to it? What are some of the limits that we can play around with this? Well, let's keep it around Earth. Our R changes. Let's play around with A. Let's play around with our semi-major axis. So if we were to do that, there are 3 values that come to mind. We have 0, R, and infinity. And let's go through each one of these. So when our semi-major axis is 0, we get nonsense. That is because it's going to be very boring. When our semi-major axis is 0, the system is not dynamic. We are just at the center of our orbiting of our orbital system. Like I said, it's very boring, unless you got there from a non-zero number. That is very exciting, and I'm sorry that you had to go through that. R, though, is definitely worth plugging in. Let's not do it that way. I used the word limit earlier to kind of as a bit of a teaser. So if we have the limit of A as it approaches R of our equation, mu 2 over R. I'm looking at my notes again, don't mind me. A. All right. I like plugging in the original equation so that I know what I'm working with. So actually going through with it, we have mu 2 over R minus 1 over R. All right. Well, 2 minus 1 is just 1. All right, let's rewrite this to become square root of, excuse me, make that bigger, mu over R. And sure, that fits that this is the one time that I do this where I don't give myself room. So let's rewrite it. Equals square root of mu over R. And this is a significant equation. But before I slap a label on it, let's actually figure out what's going on here. So this particular setup can come up in one of two different ways. One is that we are in an elliptical orbit, and it just so happens that our radius is the same distance as the semi-major axis. Cool, there's nothing really significant about that. But if we maintain that distance throughout the entire orbit, well, maintaining a distance throughout the entire orbit, constant radius, that is a circle. So this is our circular, and this is the velocity of a circular orbit. And this is where the whole velocity versus speed thing comes in, because again, if we were in an elliptical orbit and we happen to pass through this, we have the magnitude, but it is not aligned parallel to the horizon. Whereas in a circular orbit, it is. So that makes this a significant equation. Our last value here is infinity. We'll break down what that means here in a little bit, but for right now, the limit of A as it approaches infinity. Square root of mu 2 over R minus 1 over A. Plugging that in is equal to the square root of mu 2 over R minus 1 over infinity. 1 over infinity, guess what? That's 0. So the velocity of this particular orientation is going to be the square root of 2 mu over R. All right, before I, again, slap the label on it, let's do some thinking about what's happening here. If we have a semi-major axis that is infinite, then we can go out for an infinite amount of time before the planet's gravity, before the host's gravity is able to turn us back around. And if we're going out for an infinite amount of time, an infinite distance, it sounds to me like we are escaping the host. And indeed, if I use the right color, there we go. I use the right color. That is indeed what this equation is. That is the escape velocity, which is very significant in our equation sense. So let's do this. If I were to, let's see what the circular velocity would have to be for our satellite in our orbit at the radius that it is in. So at our V circular, if we wanted to circularize our orbit, our velocity would need to be square root of 3.986 times 10 to the 5th kilometers cubed per second squared. I don't have to do that, but I will, over 16,365.424 kilometers. One of these cancels out. So our circular velocity is 4.93 kilometers per second. And similarly, let's go ahead and look at our escape velocity here. We plug in the escape as the square root of, wow, that is a large square root. Square root of 2 times 3.986. Try that again. 3.986 times 10 to the 5th. I'm not going to bother with units on this one. 16,365.424. Our escape velocity at this point in our orbit is 6.98 kilometers per second. All right. So what's happening here? What is the significance of this? I'm going to take a moment to just kind of interject something here. So, yep, sure enough, we found our circular and our escape velocities. And rather than trying to describe it how I did before, because I didn't like the way that I was describing it completely for the first time and only time during this entire series, I am instead going to take the opportunity to show you this diagram that I handily drew up that is completely to scale. So we have ourselves a circular orbit, an elliptical orbit, and an escape velocity. And we can see that for... Actually, I can show you numerically down here. Our circular velocity is a little less than... Ooh, that's a bad arrow. It's a little less than 5 kilometers per second, and our escape velocity is a little less than 7. What we have is 5 kilometers per second, a little bit more. And what this means over here is that reliably, for the same altitude, your circular velocity will always be less than your elliptical velocity, and your elliptical velocity will always be less than your V escape. Unless you're doing something like if this was your apoapsis, in which case it would be further down here, but we're not going to worry about that at the moment. It's fairly intuitive geometrically speaking. If you go faster, you can get further out. And at some point, you can get so far out that you can escape. And that is what I was trying to say. I'll let you get back to it. All right. Let's touch on one last thing. So I had said in a previous episode that if we have a negative energy, we are bounded to the planet, a negative specific energy, we are bounded to the planet. But if it is greater, then we are free to roam about the stars. So if that's the case, then our specific orbital energy should be 0 for our escape trajectory, for our escape velocity. Number 2A. Oh, well. Minus mu over 2 times infinity. With infinity in the denominator, sure enough, our escape energy is 0. That's just a nifty definition to hold on to, or a nifty thing to hold on to, really. Lastly, we have this. So if we wanted to go from a circular orbit, if I can spell circular, it's been a weird day. It's been a very weird day. We go from a circular orbit to an escape trajectory. What does that look like? So for our escape trajectory, we have the square root of 2 mu over r. All right, we can take the 2 out of there to become the square root of 2 times the square root of mu over r. And that just turns into the square root of 2 times the circular. Okay. Therefore, the velocity that we need for escape is going to be 1.41 times the circular velocity for the same distance. It is always going to be 41% more energy. 41 point something. Yeah, I'm not going to box that in green. So there you go. No matter what altitude you are at, you will always need 41% more energy, more velocity. And left as an exercise to the viewer, you can compare these two. But I think for now, I'm going to call it here, especially since I keep getting all sorts of tongue-tied. I'll see you in the next one. Thank you so much for stopping by.